I'm Mary Hall, the session chair. The Test of Time Award recognizes an outstanding paper that's deeply influenced the HPC discipline. It was introduced at the 25th anniversary SC18, and as a way of recognizing exemplary work at SC. The award this year goes to John Salmon and Mike Warren on the parallel hash-talk tree algorithm revisited, in-body algorithm revisited. So this paper describes a technique for solving in-body problems which arise in many fields, including astrophysics and chemistry. The paper presents novel algorithms for efficiently solving in-body problems on HPC platforms. So this was a paper in SC 1993. At the time, the authors, Mike was at Los Alamos Lab, and John was at Caltech. And now they're going to split this session and give their own individual presentation. So the reason this paper, so I was on the Test of Time committee, and the reason this paper was selected was that it was an exemplary application paper. In fact, it's the first application paper that's won this award. And it was, had all the elements that we'd like to see in other application papers at SC. It had efficient novel algorithms, it had theoretical complexity analysis, and experimental results on the state-of-the-art systems at the time. So with that, I will turn the session over first to John, who is now at DE Shaw, and he's going to give the first part of the presentation.
Great, thank you. So, I mean, I was really honored to, get the call. It sort of came out of the blue, an email from a member of the committee. I'm sort of humbled to be up here, and thank you to the committee for recognizing this paper. So the way this talk is going to go is it's the test of time, so we're going to split time in half. I'm going to cover 1687 to 1993, and then Mike's going to cover 1993 to 2018. Now, those of you, with a slight history background will probably guess what we mean by 1687. In 1687, the n-body problem was basically first formulated. It wasn't quite in this notation. This acceleration of a bunch of bodies is equal on each of the bodies in a collection is the sum of the forces that are applied to those bodies. The 1687 is Newton's Principia. And Newton actually solved this problem for n equals 2. He figured out that the motions of bodies, the motions of planets that obey this law, they follow conic sections, they fall on ellipses, they fall on hyperbola and parabola, the whole deal with foci of ellipses and so forth. So, problem solved with n equals 2. N equals 3 is a whole nother matter. There's no closed form solution. The solutions that do exist are often non-repeating, so it's not even that they're periodic. You won't get orbits that you come back to. And basically, as they say today, it's complicated. That's just for n equals 3. So let's fast forward, 200 and 300 and something years, 200 and something years. So in 1941, Erich Holmberg, in 1941, it was recognized that this problem requires order n squared arithmetic to do. If you want to solve this problem, you have to add up all n forces on n particles. So it's about order n squared. It's 1941. Turing hasn't even invented the computer yet. Nevertheless, Erich Holmberg, a professor at Lund University in Sweden, decides that the time has come to solve the n equals 74 problem. He's interested in how galaxies form, and he thinks 74 particles will probably get him some sense of how galaxy disks form. Astrophysical Journal, 1941. How does he do this? He uses photocells, galvanometers, and movable light bulbs. He actually does the force summation by adding up the amount of light that impinges on a bunch of photocells that he keeps on a desktop, and he does the time integration, presumably in a notebook with hand arithmetic. And he wrote, and he moves the particles around, and he gets these beautiful pictures on the right where you actually see tidal disks forming. So this was a tour de force of 1941. This is the n-body problem in 1941. We talk about reproducibility a lot at supercomputing. Turns out there must be something in the water in the Nordic countries. Turns out that students at Oulu University in Finland in 2014 decided they really needed to reproduce this work. So they got a tabletop, they got some photocells, I think they did the time integration with a computer, but they moved light bulbs around on a table, and they actually took pictures this time so we can see the result. Okay, let's fast forward to 1953. We have an n-body simulation finally done on a computer. This is the famous Metropolis paper. It's the first n-body problem done on a computer. It's also the first instance of the Metropolis algorithm on a computer. They're doing 56 particles, and it takes about 3 minutes per time step. Fast forward another 10 years. Sverre Arseth decides to reinvestigate the clusters of galaxies problem, and he manages to get up to n of 100 on an IBM 7090 running 100 kiloflops with an order n squared algorithm. Okay, so now let's go back to that order n squared algorithm. N squared is just really bad. So what we're going to do to make it better is first we're going to make it worse. We took something that you could actually, a high school student could write the program to solve the top equation. But we're going to turn that into something else. We're going to turn it into the gradient of a convolution evaluated at endpoints. This really doesn't seem like a step in the right direction. But you can reuse another theorem. You can use the Fourier convolution theorem. It says that the convolution of f and g is the inverse Fourier transform of the Fourier transform of f times the Fourier transform of g. And now, all we have to do is compute Fourier transforms. Well, that's still hard. That still looks like order n squared until Cooley and Tukey come along in 1965 and tell us that we can do that in order n log n time. So suddenly, this problem became an order n log n problem. And only 4 years later, Hockney and Hole are doing 200,000 stars doing galaxy formation with 200,000 stars. It's a 2D problem. They're doing it on a 64 by 64 grid on a CDC 6600, and they're doing, again, it seems like we can never get below about like a couple of minutes per time step. The other interesting thing is that this 1969 paper almost invents tree codes, which we'll come to in a moment, and are actually what we use in our paper, and basically what everybody uses today. They came this close to inventing tree codes, but they said, well, we can do this sort of funny operation. We can go one level down. They did that. They remark in the paper that they could go a second level down and get another order of magnitude improvement, but they didn't bother. And I can only imagine, because they're writing in a computer language that doesn't have recursion, it never occurred to them to do recursion on this. So these Fourier methods are great, but the spatial resolution is limited by the grid. So they had a 64 squared grid, so you can only do basically, you can only resolve things that are about a 64th the size of your system. Andrew Appel, in 1981, decides he can do better. He builds a clustering hierarchy. He actually builds a tree. He puts all the particles in a tree where one cell of the tree is inherited from the ones above. And he remembers, going back to 1687 again, he remembers Newton's theorem 36, here written in Latin for all of us who follow the Latin. But basically, Newton figured out that gravitating spheres are equivalent to point masses. If you have a sphere, you might as well just take all the mass and put it at its center. He figured this out for the Earth and apples and the moon and the planets and the sun and so forth. And Appel writes two recursive functions. Beautifully elegant, completely straightforward recursive functions. If you want to compute the force on something, well, you either say, yeah, I like it, I'll do the force between those two things, or instead, I'll split them into pieces and I'll do the forces between the pieces. And basically, it's like a mic drop. Okay, this changes the problem from n squared to order n, and the best part of this is in his Princeton University undergraduate thesis. So nobody pays any attention. he actually writes a Scion paper, which is a beautiful piece of work, which finally gets published in 1985. Barnes and Hutt come along in 1986, and they change the way you build the tree, but otherwise they do pretty much the same thing. They're doing 4,000 particles suddenly. It's a 10x improvement, and they have this theta parameter, which they set to 1.0. And again, we're doing 6 minutes per time step. They're on a VAX 780. A year later, Greengard and Rocklin come along. They have an order n algorithm, which is actually just like Appel's algorithm, but they use higher order multiples, and the big thing they bring to the table is precise error bounds. The previous work had all been kind of, well, this looks like it's a pretty good approximation, let's use it. Greengard and Rocklin, they're hardcore mathematicians. They don't give you an approximation unless they give you an error bound with it. The downside is that it's actually pretty expensive, especially in 3D. That was actually repaired in subsequent papers over the next few years, but as written, it's a big constant times the order n. And it's kind of hard to see how to build an adaptive grid, though again, that was also repaired in subsequent years. Okay, so finally, I get to come to the party. I came to Caltech in 83. Just as Jeffrey Fox and Chuck Seitz were building the Cosmic Cube, which was a 64-node, 8086, 8087 machine made of wire-wrapped boards in a long row, sat on a table in the lab, and a bunch of us in Jeffrey's group were writing programs to do parallel calculations. Shortly thereafter, N-Cube comes along and actually starts selling machines. This is a work of art. This is 64 nodes of the N-Cube 10, which you could buy up to 1,000 nodes. So 16 of those boards would go in a chassis. Each node consists of one CPU chip with communication and 6 memory chips and nothing else. And it sits on a board, and I couldn't find any pictures of this online. So I asked my wife to help me, could you help me find some of these on Google? And she says, we have one in the basement. So this picture is the one from the basement. In 1991, Intel installed the Delta machine, 512 nodes at Caltech. There also aren't very many pictures of this, which I thought was kind of surprising. And this started winning Gordon Bell prizes and so forth. This was a big deal. This was the machine that was really, I think, the one that was first demonstrating that you could do big parallel computations, big scientific computations. Mike, I met, I think, in 1986. Basically, he walks into my office in 1986. He says, Jeffrey Fox told me I should talk to you. You got anything to do? And I'm working on the Fourier codes at that point. And Mike sets out to write a tree code. Mike and I, in 1992, won the Gordon Bell Prize for the work on the Intel Delta. Remember previously we were in the thousands of particles. We're now at 8 million particles. And we're still running at 77 seconds per time step, so you just can't get it below a minute. We have a parallel Barnes-Hutt code, and we're up to 8 million particles. Okay, that's the history leading up to the paper. So I think there are 4 nice things in this paper. As I went back and read it 25 years later, I think there are 4 nice things in it. We have improved accuracy, we have a new representation of the tree, we have space-filling curves, and we have a latency hiding and cache-friendly tree traversal. So the accuracy. Barnes and Hutt said you use the multipole approximation when some funny geometric quantity, S, the size of the cell that you're looking at, divided by the distance to the cell is less than theta. And theta was some global constant that they just said, well, how about 1? And then people later said, 1's a little high, how about 0.7? So standard practice around then was 0.7. And we thought we had a bug. We ran a galaxy simulation that the galaxy just blew up. Turns out that no, there wasn't a bug in the code. There was a bug in our understanding. Errors are unbounded in the Barnes-Hutt simulation if theta is bigger than 1 over square root of 3. So that kind of got us to scratch our heads. And we thought, maybe this Greengard and Rocklin idea of having tight error bounds, maybe there's something to that. So we did a little work, and we figured out what the error bounds would be. And we modified the code so that you keep refining the tree until the total error satisfies some criterion. And after all of that, our worst case errors went down by a factor of between 3 and 12. Our RMS errors were either the same or got about up to 2 times better. We got about 60% of the operation count, so we were doing 40% less work to get these better errors. And that's all compared to a quadrupole Barnes-Hut code with theta equals 0.65. So that was one of the things that's in the paper. But there's a cost. That paper from the previous year, well, okay, you don't know when to stop now until you're running. You're looking, you're descending this tree, you're saying, can I use this, can I use this, can I use this? And you don't know whether you're done with that until you've actually decided to do the calculation. And the code that we had written over the previous few years, it was just never going to do that. So Mike basically said, well, let's just start over. Got nothing better to do. So we start over. We started with the old tree representation. We took a tree that looked like this, right? We have a collection of boxes in 3 dimensions. And what are the kinds of things you need to do with this data structure? Well, you need to find the parent of an object. You need to find the children of an object. You need to read and write the contents of what's in that object, right? So, we're C programmers. We're kind of naive. Just like everyone else, what do? You follow the pointers, right? You make a structure. It's got a cell pointer to the parent. It's got 8 pointers to children. It's got the mass and the cutoff and the quadrupole moment and whatnot. And there's your data structure. Well, the problem with that, there's a bunch of problems with that. One is that pointers don't work across nodes. Another is that it has bad spatial locality. So here's the second thing we did in this paper. We said, let's not follow pointers. Let's make a new representation for the tree. So let's just decide to number every possible cell in every possible quad tree or oct tree. We don't have to actually have them all in memory, but we'll just know that there's a number for each one that we do want. The root cell has key 1. And the keys of any of the children of any cell in the tree you can obtain by left-shifting the key and adding in 2 dimensions 0 through 3, in 3 dimensions 0 through 7. And to go for the parent, if you have the key of a cell and you want to find its parent, we'll just right-shift by the number of dimensions, 2 or 3. So you can see in this picture, if you follow the arrows down, you can see that that's actually the rule that's being applied. Bodies have keys too. So there are cells and there are bodies. Bodies have keys too. You right-shift to get the keys of the cells that contain a body. If you have 64-bit keys, remember it's 1993, we didn't actually have 64-bit integers, but we slap 2 32-bit integers together, you can have a 64-bit key. Well, now you can have a maximum tree depth of 20, which gives you a density dynamic range of about 10 to the 18, which is actually just plenty. So a 64-bit key gives you a terrific representation of the kinds of structures that we need to do to study astrophysics. Okay, great. We know the key, we know the parents we know the parent keys, we know the child keys. We have this lovely little abstraction, but where does it actually go in memory? Well, now we just pull something off the shelf of standard computer science, and we say, let's put it in a hash table. So we make a hash table with 2 to the h entries, and we make a completely trivial hash function. The most simple hash function you could possibly imagine, just take the least significant bits of the key, that's your hash function. We used an open hash table, so there's a chain of cells at every location in the table. You get spatial locality within levels. You get spatial non-locality between levels, so as you go up and down a tree, you're at a completely different part of the hash table. That's nice. And you get temporal locality by moving recently accessed things to the front of the chain. So this is all working really nicely with the cache structure of our machine. And now we have to ask the question that we always ask when we do parallel computing. It's not just what do I do, but which processor is actually going to do it. So which processor is going to compute the force on each particle? Which processor is going to compute the center of mass? Which processor, who do we ask when I need the center of mass of some other cell that I don't actually have? I have to go ask somebody, who's that going to be? And these things change over time. The system evolves, these systems move, so that's actually going to be a dynamic process. And the answer here is another of the things that was really fun in this paper, space filling curves. So these curves have been around for I don't know, late 19th century, I guess, you can build a continuous curve that fills space in 2 or 3 or more dimensions. And what this curve has the property of is that nearby on the curve is usually at least nearby in space, right? If you move your finger along this curve, you can see that you're moving mostly continuously, mostly if you're near on the curve, you're near in space. Occasionally there are these big jumps. Turns out that that's a natural consequence of the key representation that we had on the previous slides. If you sort the keys the way we constructed them on the previous slide, then put them in sorted order and see where they go in space, they'll actually follow exactly this Morton order space-filling curve. You can do even slightly better if you tweak the way the keys, you construct them, you tweak the order that you add 0 through 7, you can actually make it always continuous in space. And that's called Peano-Hilbert curve. So finally, this is the picture that you get. If you take, this is actually a highly clustered collection of particles. This is 10,000 particles that are, some are very, very close together, and others are spread out far and wide. And if you just sort them in the Morton order, in the Peano-Hilbert order, so you make their keys and you sort them in Peano-Hilbert order and then draw the line between them, well, you get this lovely curve that sort of looks like a traveling salesman problem. It actually just follows the dense parts and it stays within them, and then it moves to the next one and it stays within. And now you have a natural way to do parallel decomposition. All you do is you take that curve, you take that sorted list, and you break it up into however many processors you have. So I broke it up into 200 processors, so each one has roughly 50 points in it. And if you look at the colors, I mean, it's you know, only a physicist could come up with colors like that, or someone colorblind. But in any case, if you look at those colors, you'll see that the regions are mostly surrounded by only 3 or 4 other colors. So, you know, a blue section has a green and a yellow and a magenta section near it and not much else. So you have this terrific spatial locality that is what you actually want from a parallel decomposition, and it comes to you free almost from using the space-filling curve. Okay, there's one last thing we did. Well, recursion is elegant and beautiful and clean and neat, and it hides all the details. And there's nowhere to get in and get a hook on how can I do something differently or better. So the other thing we did was we rewrote the recursive function as an iterative function. So basically, standard breadth-first search of a tree. We're going to compute the forces on a body. Well, we start at the root, and while candidates consist of the root, while we still have more candidates that we might open, well, we look at them and we say, should I open it? If I should, I add the children to the candidates. If I shouldn't, I do the arithmetic, compute the interaction. Okay, well, that's kind of slow because it turns out that the computer actually computes interactions really well a whole lot at a time, so you vectorize that. So we make an interactions list, and instead of saying compute the interaction, we just take that pair and put it on the interactions list, and then at the very end, we just run through that list as fast as we can. Okay, well, now we're basically done with a parallel algorithm. We can now run this code in parallel. All we have to add is the code in red that says, as we're traversing this tree, if that cell is not here, if it doesn't have some here bit set, well, I send an RPC request out to the guy who does have it, get the result back, and carry on. This works, but it's terribly, terribly intolerant of latency, because sending out an interprocessor RPC takes, I don't know, half an hour, 2 hours, whatever, some really long amount of time. So one more modification of the code, one more rewrite. We build a deferred list, and when the thing is not here, we put the thing that we need on a deferred list, and then every once in a while, every time through the loop, we get to the end of the loop, and we've hidden a lot of hair in interprocessor communication happens here in red near the bottom, but we've basically now overlapped communication and calculation, and we can carry on with our work while communication is happening in the background, and we suddenly have a latency-tolerant algorithm. One more level of latency tolerance is to wrap the whole thing in a loop that keeps a working set of bodies active concurrently. If you make the working set really big, well, now you can tolerate a lot of latency. This is basically what GPUs do today. But if you make it too big, we didn't have GPUs then, we had small caches and small machines. If you make it too big, you blow out your caches and you lose performance again. So in practice, it was just a matter of tuning a number and seeing if it worked right. And about 30 worked really well on the Delta. So that's through 1993. One more thing. We took the code, which had been strictly a gravitational code, and we basically factored out three sort of key parts. The things you need to do are you need to populate a parent cell with what's in its children. You need to do that acceptability criterion, decide whether to use an interaction, and you need to do the interaction. So we factored those out, and we were able to use the same code to do a whole bunch of different things, some of which Mike is going to tell you about. This picture is of vortex dynamics that we did with Gregoire Winkelmans and Tony Leonard at Caltech around the same time. So I'm going to finish my part by thanking a few of my mentors and colleagues. As I look back over this, I feel like I was really lucky to have terrific mentors and colleagues all throughout my career. So Jeffrey Fox was my advisor at Caltech. He was the one who set me on the problem of actually doing astrophysics and using parallel computers. I did that work in close collaboration with Peter Quinn, who was at Caltech at the time and is now at IRAR in Western Australia. Paul Messina took over the Center for Research in Parallel Computation, helped to bring the Delta to Caltech, kept me working on this stuff for several more years. Without him, we wouldn't have had the Gordon Bell Prizes and the work on the Delta. And now I'll step just a little outside my little historical window and talk about the last 25 years. Shortly after this paper, I started working a lot on Beowulfs, and that was thanks to Thomas Sterling. So, big thanks to him for keeping me involved in that. And finally, for the last 10 or so years, I've been working with David Shaw at D.E. Shaw Research. So I used to do simulations that had 10 to the 10 solar masses, gigayears, and megaparsecs. Those were the scales. And so now I do simulations that have angstroms, femtoseconds, and atomic mass units. So we do molecular dynamics now. And with that, I will hand it over to Mike.
Thanks, John. So we're up to 1993. So I wanted to give you some context to actually remember that time in the world. So supercomputing that year was in Portland, Oregon. It was the second release of the top 500 list. The numerical wind tunnel with 160 Fujitsu vector processors was -- 1 on the list. The connection machine 5 with 1,024 nodes was at Los Alamos at #2. At that conference, the draft of the Mpi Standard was introduced. Mpi didn't actually exist yet. It wasn't finalized until the next year. So this code was being written in the context of we did not have a standard message passing library. Every machine had a different communication library that you would have to port the code to. If you were working at a national lab, you probably had a Spark station on your desk. It was hooked up with 10BASE-T Ethernet. The rest of the world was just being introduced to the Intel Pentium. People were working away. Linux wasn't yet to version 1.0. The same week as supercomputing in Portland, the Mosaic web browser version 1 was released for Microsoft Windows. And we were all connecting to the internet with 19.2 kilobaud modems. So a lot of the things you see that we were doing are commonplace now, but at that time in the world, parallel computing was new, everything was fresh, and this was the state of my mind at that time. So I was in the 5th year of graduate school at Santa Barbara. I was in the theoretical division at Los Alamos. John and I had won the Gordon Bell Prize the previous year with the version of the tree code that had been ported directly from the Barnes and Hutt code. So I'm a graduate student in physics. I need to discover something new about the universe in order to get a PhD. It was not my mission to write a new parallel algorithm. So I'm unhappy because our simulations are broken. You know, galaxies are exploding for no reason. I'm unhappy because the compilers are broken. They can't optimize anything at all. C++ is a hopeless wreck of not being able to do things. The operating system on every machine is different. You've got, you know, one on Suns, one on IBMs, one on the N-Cube, something else on Intel. The file systems are a complete disaster. We're generating a huge amount of data with these simulations, and we actually have to do something with it. And constantly fighting with file systems. And then finally, the hardware was often not functioning correctly. So you may write some code and run it, and it doesn't work, and you spend the day trying to debug it only to find out that there's a bad node in the machine, because it's very hard to debug a parallel process when you've got lots of stuff going on at the same time. So kind of the context for the creation of this code was that, you know, I was trying to do physics. I was spending all day with a very brittle and sort of finicky piece of code littered with if-defs that had pieces bolted onto it over the years. And I really wanted to do something new. So just as an aside, I think supercomputing is an inherently interdisciplinary field. You have scientists trying to understand the world. You have mathematicians trying to prove conjectures about the world. Computer scientists understanding the foundations of information and computation and actually creating complexity from very simple things like bits. And then software engineers who are trying to apply all this established knowledge to create a program and manage all of this complexity. So I think it was a very unique pairing that both John and I had Jeffrey Fox as an advisor. I was an undergraduate, John was a graduate student, but I came to Caltech knowing that I wanted to do physics, but I was very interested in computing. So I'd already had that interdisciplinary mindset, and I discovered, John as a mentor shared very much that same sort of approach and background. So both of us were all four of these things, and it was an incredibly powerful partnership where John was very careful, very mathematically oriented, could prove a theorem and do error bounds with incredible applied math. I could take a piece of code and sit down and actually write the assembly code to make it go as fast as possible. And kind of our strengths and weaknesses really complemented each other. But overall, the goals of this design, I know now there are just a few times in a programmer's life where you actually have a green field, where you're not constrained by pre-existing APIs and problems. So as a graduate student, not being paid very much, no one really depending on your output, I had kind of a short window of time to actually architect and write a code like I thought it should be done. So we wanted to be simple. We wanted to isolate physics. We wanted all of these very sort of obvious sorts of things that were not present in this older code. And one of them, I think, most important was this idea of overlapping communication and computation. And there were actually two parts of that. In the previous version of the code, the domain decomposition and communication all happened at the beginning of a time step. And then for all of the time after that in the time step, every node might as well have been a sequential computer. It was running exactly the same code because we'd communicated all the data it would ever need to complete that time step. So if all your communication is only happening in a small fraction of the time, obviously you're not getting the most out of that very expensive communication network. You'd be much better off if you could spread out that computation over a longer time. So this approach that John described in the code, with a lot of this deferred work, allowed us to communicate over the full time step, which was a bandwidth improvement. And then the second part of that was latency hiding, where in the inner parts of the loops, you wouldn't have to continue to stall and wait for data to come in. So the end result was a code, and the paper was published in 1993. The inner loop was something that the performance was very dependent on. So this is later in sort of the SSE3 days, but there's about the code that I have personally run has probably executed the instructions you've seen here, something on the order of a few times 10 to the 20th times. So that was isolating the work that's being done for all of these algorithms to just this very small piece of code, which everything else existed, so that could run as fast as possible. So the bottom of this table is 1993 at Caltech on the Intel Delta. It was 10 gigaflops on that machine. So I presented here at the Supercomputing Conference 4 years ago a somewhat refined version of the same code. It was changes at the level of 5 or 10% in terms of lines of code, ran at 7 petaflops on Titan. So this piece of software was elastic over a factor of 1,000,000 in performance over those years. And there were a lot of challenges along the way getting it to run on these machines, but it has really been a fixture in terms of understanding how to scale these physics problems to larger and larger scales. So this is a plot kind of just showing particle number versus time and the exponential growth that's happened. So there have been a number of different techniques. A direct implementation with a double loop, you see kind of prior to 1980 was the favorite method to do physics. Through the 90s, a number of Gordon Bell Prizes have been given for n-body applications. And then finally, as we get into the 2012, 2014 timescale, these codes are at the trillion particle level. So, kind of beyond just doing the physics with this code, something it was very much used for was actually proving new technology. So in 1997, we had kind of the convergence of two things, creating the context where we won the 1997 Gordon Bell Prize for performance on ASCII Red with this code, and at the same time for price performance on a Beowulf cluster, which had actually the highest performance there was about 2 gigaflops, which was made out of the two machines, one of which you can see in the picture here. That's me at Supercomputing 96 in Pittsburgh with a 16 processor Beowulf cluster. You can see there behind me is the similar space filling curve that you've seen a number of times on the images today. So that machine there was about a gigaflop on 16 Pentium Pro processors. Sort of, if you could turn the camera around and look the other way, you'd see a very similar machine at the Caltech booth. And those two machines were actually connected together. We actually crimped 16 Ethernet cables and ran them under the walkway between the two booths to make a 32 processor machine that ran at 2 gigaflops, which was the Gordon Bell Prize winner the next year. And of course, if you know the rules about the show floor, that was an unauthorized network connection, and Caltech had to pick up the fine for that. But I know several people like to tell that story, and the fine has paid for itself many times over. But the picture there in the middle is later at Los Alamos, where we become very concerned about the power usage of these processors, and looking at the scaling that was, power densities kind of like a nuclear reactor at the surface of these microprocessors. So that was the Green Destiny project, and you can see me there under the word Beowulf next to Gordon Bell, and then Linus Torvalds there in the front. But this kind of set the stage. These machines, commodity microprocessors, Linux operating system, parallel computing, that was the basis of what we have now essentially in HPC. All of the top 500 run Linux. Actually, the very first machine running Linux on the top 500 list was the 1998. We built a machine out of DEC alphas at Los Alamos. So that was the first machine running Linux on the top 500. And then last year was the last holdouts, and 500 of 500 were running Linux. But this is the same architecture as you'll find in the cloud on AWS or Google Compute Engine. You can log into one of those nodes, and your Unix environment from 1993 is right there with all of the tools available. So I want to go through kind of some of the physics that we did with this code. It was very flexible, and it really was also a kind of the vanguard of simulation becoming a true fundamental part of the scientific method. Originally you had experiments and theories, but now simulation is really a fundamental part of how you tie those together. Our understanding of the universe, we can't run experiments on the whole universe and wait 13 billion years for it to turn out. But we have a set of physical laws, and we have ideas of the initial state of the universe. So if our understanding of that physics is correct, we ought to be able to start it at the beginning, follow those rules, and create something that looks like what we see in telescopes. So this is a representation of the cosmic microwave background as it would be seen through one of the trillion particle simulations we did in 2014, compared with the similar results from the Planck satellite. And in this particular representation, they don't look very similar, but a lot of that has to do with sources of noise that exist in our galaxy that have not been included in the simulation. So a few other applications that were published. This code could also do hydrodynamics, so not a long-range force, but short-range, but finding the particles that are near a particle to update the pressure variables. We used a technique called smooth particle hydrodynamics, and that fit very naturally into this framework. So anywhere you had hydrodynamics and gravity, the code was very much applicable. You could do things like smash protoplanets together. Leading theory of the origin of the moon is that actually a proto-Earth collided with an object around the size of Mars, and the moon is the result of the debris that came out of that collision. We were able to simulate the comet that impacted Jupiter, highly hypersonic fluid dynamics problem. In 2005, I had an intern undergraduate come out and simulate the Deep Impact mission, which was NASA flew a satellite into a comet and watched all of the debris coming out to understand what was there. Sam will reappear in this Sam Skillman will reappear in this story again. The first stars combining hydrodynamics and gravity. And we actually did some work in biological systems because it's the same electromagnetic forces, particularly in water, which has a dipole, which is long-range interaction in these biological systems. So this is a ribosome. So as you have these large biomolecules, having it in a bath of water where you can't just cut off the forces at an arbitrary length, these sorts of codes are very useful. And as John mentioned before, the work with incompressible fluid flow, so that was published in the Journal of Computational Physics. There was work, the first simulations of a core collapse supernova in 3 dimensions were done with this code by Chris Fryer and I at Los Alamos. This is work from just this summer studying the formation of Uranus was the result of one of these giant collisions. And we know this because the planet is completely tilted over on its axis. So through a big series of these simulations that were done by the group of collaborators, they're actually understanding the origin of that system. So there's also, beyond physics, this is an excellent data structure to look at anything that involves kind of pairwise similarities or distances. So neighbor finding, kernel summations, correlation functions. There's in fact one of the papers that cites the 93 paper that itself has one of the largest number of citations is very recent in machine learning using Barnes-Hut type algorithms to do stochastic neighbor embeddings to visualize these high dimensional machine learning models. So I've sprinkled a few quotes through the presentation. My own effort on Twitter is that a supercomputer is a device for storing obsolete software libraries. As time goes on, it seems like the hardware is changing at a very rapid pace, but the software is not changing so quickly, and depending on when your code came into existence, these software libraries may persist for a very, very long time on these supercomputers to provide the environment they expect. So kind of our mindset in 1993, parallel computing was very new. We wanted things to be simple. Our code basically assumed nothing would work. We had our own data format. We sprinkled tests throughout the code, checking things that could never be wrong. And occasionally you would find that the mass of the universe had changed. And that actually made the code quite useful for tracking down bad hardware. But kind of when I see the present day, it's not in the theme of simplicity. It's the theme of what can we possibly do to make these machines faster. A reason we were successful in 1993 is that microprocessors could do things that the Cray vector supercomputers could not. The vectors in the Cray were just too long to be efficient for a lot of these dynamic sorts of problems. So those Cray vectors were 64 words long, and now we're talking about GPUs and vector coprocessors with that same vector length. So we're coming full circle, and not only having that complexity, but very deep pipelines, having distributed shared memory, having a hybrid architecture where not only do you have to understand MPI, but you have to understand shared memory programming and moving data from multiple levels of the memory hierarchy. And from my perspective, the success at exascale is not about building hardware, it's about the software and the problems that need to drive that process. So I want to keep everyone honest and make sure that the applications of the future are not driven by the hardware that's available, but let's make the hardware do the problems that are valuable. So to wrap up, this model of having a system of the world, the evolution of the universe is shown there in the yellow box. It's a double loop for 13.7 billion years, and you integrate it over time. There's lots of problems in the world that are very much of that flavor. And the company I founded 4 years ago, Descartes Labs, is very much using supercomputing and everything I've learned over my career to apply these techniques, the ability to process petabytes of data and turn it into information and analytics that are actually valuable is what I'm doing now, and I'm happy to not be alone in that endeavor. The people you see there were from last month in Taos, New Mexico. We got the whole company together. We've grown from 6 to over 90 at this point in less than 4 years. Sam Skillman, my intern at Los Alamos in 2005, was our first hire for the head of engineering there. So Sam's here in the audience and is now kind of taking the flag for the next generation of supercomputing and applying it to the world. So to conclude, I'm just going to take the conclusion from the paper, which I think still stands up very well. This code didn't evolve from a pre-existing sequential algorithm. It needed a lot of school of hard knocks to understand what was important in the design, and that the power of computing is really unprecedented and incredible, and these types of codes and models and algorithms are really the key to understanding the complex physical systems in the world and making progress. So like John, I want to thank Jeffrey Fox at Caltech. Peter Quinn and Wojciech Zurek were the astrophysicists who kind of gave us this problem to start out with. Paul Messina at Caltech. At the time in 1993 when I was doing this work, we were supported by a NASA HPCC program, which is how we got in contact with Tom Sterling and kind of jump-started the whole Beowulf process. And I think I'd like at least to take some credit for the success of these systems, because back in those early days, it wasn't clear that they were going to be good for anything. And John and I showed that, yes, indeed, you can take a code that is not a simple code that's purely vector and do things with it and make it powerful, and that these machines were a valuable resource. So, and also thank you very much to the committee and the nominators for this recognition. I'm really truly honored, and I'll close with a quote from Donald Knuth, which I think really captures my life in both physics and computing, and that science is what we understand well enough to explain to a computer, and art is everything else we do.
Please join me in congratulating John and Mike on their amazing paper and excellent presentation that showed us that the committee made the right choice. And why don't you, John, also come up and we'll take some questions from the audience. Let's thank the speakers first.
If you were starting from scratch again today, how would you write it differently? What have you learned over 20, 30 years that if you were really doing it all over again on state-of-the-art systems like we have today, how would it be different?
It wouldn't be different.
Or should we stop at 2:30?
Somehow, I think we used the right architecture. This code was ported to GPUs on Titan. I'm not a fan of GPUs. I don't like hardware that breaks existing APIs because I think programmers are very expensive, and people who build hardware that break the output of programmers, that's very, very expensive. We got 80 million core hours on Titan to do cosmology, and I worked out the math. That's several $1 million worth of computing time, and that justified me spending 6 months to make the kind of inner loops of the code work on GPUs, and I knew that code would never be used again. But the mere fact that it was 6 months of work to do that, there are codes out there that still have not been ported to GPU architectures after years of effort. So the flexibility kind of at the low level to kind of, it came down a lot to the fact that these interaction lists had a lot of commonality as you traverse through the tree. So the memory bandwidth requirement was much, much lower than you would expect otherwise. So that really worked around the fundamental limitation of moving data over the PCI bus to where you had a faster processor.
I think, I'll plug what I currently have. I'm fortunate enough to work on special purpose hardware. So D.E. Shaw research has sort of found a problem that is, we hope at least, so valuable that it's worth actually spending the time and effort to not just break the APIs, but to actually build our own hardware. So if I had to do it all over again and I had unlimited resources, I would build special purpose hardware to do it. But not everyone is fortunate enough to have that.
Yeah, I have a question.
Last question.
So the original simulation problem you solved involves particles that are distributed across space in the regions of high and low density. Now we also have CFD and molecular dynamics, which have a much more even distribution in space. And I wondered what lessons you take from this that can optimize solutions of that type.
So one thing I think we've, as you know, we don't do these tree codes for molecular dynamics typically because these tree codes are astoundingly good at highly irregular systems, and it's very, very hard to beat the FFT. I mean, it's not just order n log n, it's 5 n log n, and you just cannot beat that if that serves your purposes, if that satisfies your needs. So these types of codes are fantastic when the world is non-uniform.
And they work fine if it is uniform.
They work perfectly well if it is uniform.